Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss approximating solutions to the heat and wave equations in 2 and 3 dimensions. So in this topic we will discuss the heat and wave equations in 2 and 3 dimensions. We will look at how we would proceed with such simulations. So we will discuss taking a 2-dimensional or 3-dimensional region and approximating it by a grid, and then going forward one time step into the future. We will focus on examples, however, of finite difference approximations of problems in these two areas, and we will not be looking at implementations. This is something that is left to the viewer. It's challenging, requires an appropriate number of useful data structures, but is nevertheless satisfying once completed. Laplace's equation is reasonably straightforward. It simply says that the Laplacian of a real valued function of a possibly vector variable is equal to 0 everywhere. This says essentially that at every single point of interest, the sum of the concavities is equal to 0. Now, you will recall that concavities are proportional to acceleration and force is proportional to acceleration. Consequently, this is essentially saying at every single point, all of the forces at each point are balanced. So, if all of the forces are balanced, there will be no change to any velocity within the system, and if the system is not moving, it will remain in a steady state. We'll be examining this last case. Now in one dimension, Laplace's equation says that the second derivative with respect to the one variable is equal to 0. Well, that essentially says at best u of x can be a straight line, and that's about it. So u of x must be of the form ax plus b. Now suppose that we have this circuit board. We have two processors on this circuit board, and shown in black, and we have the circuit board connected to a heat sink shown in light blue. Now the circuit board initially is at ambient temperature, and the heat sink will actually maintain the area around where it is connected to the circuit board at the ambient temperature. However, when the processor is turned on and the circuit is being used, the processors will start to create heat throughout the system. So what we're going to do is we're going to approximate the system. So we're going to assume that the edges of the circuit board, which are probably not touching anything, can be considered to be insulated, as air is a reasonably good insulator. On top of that, the heat sink, shown as 4 dots in the top left in light blue, are maintained at ambient temperature. Suppose the processor in the lower right, shown as 4 red dots, is more of a central processing unit and therefore maybe generating more power, whereas the processor on the left may be some sort of floating point unit which isn't used as often and therefore may be generating less heat. However, when this unit is turned on, the entire circuit board is initially at ambient temperature. However, with the processors running, they will start to produce heat, and that heat will start to travel through the circuit board. The question is the heat going to accumulate to the point that it's actually going to damage that circuit board? Or is the one heat sink that we have sufficient to keep the board cool? Now you'll notice that the heat sink is actually closer to what is the warmer of the two processors, but we'd have to run a simulation to see whether or not it is indeed appropriate. Now here's a pool, and you can consider the surface of the pool as a two-dimensional object. And the borders of the pool, assuming they're solid like concrete as opposed to sand, they too can be considered to be insulated. Now suppose at that point, at time t equals 0, we throw a rock into the pool at that point. Well, of course, the rock is going to generate waves, and those waves are then going to expand out and reflect off of the border. So what is this going to look like, and what is the pattern of waves that will occur? What we're going to do here as well is we will consider all the points that are not in the water to be insulating points, whereas all of the white dots are considered to be within the pool. Notice we are approximating the pool with a grid. So it's not a great approximation, but we could, of course, increase the density of points in the grid if we wanted a better approximation. And humorously enough, it's actually not going to be that terrible an approximation, even with such a coarse grid. Of course, a more finer grid with more points will give a better approximation, but that will require more processing time. So if we know the scalar values, be it temperature, voltage, or wave amplitude, at every single point in our two-dimensional domain at time t0, so for example, the temperature may be ambient, the voltage may be 0, the wave amplitude may be 0, we have a smooth pond. At that point, we will then use our finite difference approximation of the corresponding equation, heat or wave, to estimate the temperature, voltage, or wave amplitude one time step into the future. This is exactly what we did in one dimension, only now we will do it for every single point in the domain in our two-dimensional world. Visualizing this, suppose we don't know, or we do not currently have at least an approximation of u at the point ij at the time l plus 1. Well, if we know all the values or the state at time t sub l, then we can just substitute all those 5 values into the expression above, and that will be our estimate one time step into the future. All we have to do now is do this for every single point in the domain at the next time step, and then we know what the state looks like one time step into the future. The 5 previous values may be estimates that were previously made, or they may be boundary values. And of course, we may have to modify it if they are insulated values. So if there is an insulated value, for example, below assume that u sub I j minus 1L is insulated, then we assume that u sub ijl actually equals that insulated value in the equation, and thus we eliminate both the term and the corresponding impact on uijl in that equation. So here we see that u sub I j minus 1L has been eliminated, and the coefficient in front of uijl has been reduced to 3. If that was a boundary value, we would instead substitute the value and leave the coefficient of u sub ijl unchanged. Now, for the wave equation, we just need one more item of information to calculate the next value. So once again, on the right, we see u sub ij l plus 1, which is the value we'd like to approximate. However, to approximate this correctly, we also need u sub ij L minus 1, information that was not necessary, as we saw before, for the heat equation. Apart from that, everything else is more or less the same. And as you may suspect, just like when we were at the very first step, approximating the solution when L is equal to 1, we had to instead use the second initial condition, the initial velocity, to approximate or to substitute into that expression to make that first approximation. After that, we just continued to use this formula because we always knew all estimates at either at L or at L minus 1. It's only when L is equal to 1 or L is equal to 0 when we are estimating the value at L equals 1 that we needed the initial rate of change of the amplitude. So it's more or less the same. Now, once again, these are the heat and wave equations. And in 3 dimensions, we will now have 3 values, x sub I, y sub j, and z sub k, at time t sub L, and we will approximate the value at this place in space and time with an unknown u sub I, j, k, L. Probably doesn't take that much to figure out that if with a heat equation we just once again make all of the same substitutions as we did before, and we now get this equation. And so this equation tells us what the state will be one time step in the future, and it depends on the previous value plus a linear combination of surrounding values. The same is true for the wave equation, except now rather than taking all 4 adjacent values, we are taking into consideration all 6 adjacent values, 2 in the x direction, 2 adjacent values in the y direction, and 2 adjacent values in the z direction. All right, suppose we have a piece of metal, and the center of that piece of metal is heated to 1 degree Celsius, whereas the border is maintained at 0 degrees, and the initial state of every other point on that piece of metal is also 0 degrees. So it's in contact with a large, well, perhaps ice at the boundaries. What happens over time is that the heat is going to dissipate throughout the region and it will be absorbed by the boundaries. And so the heat will approach the temperature of the boundaries, which is 0. Here, on the other hand, we have a sheet of metal with 2 points, one point heated to 5 degrees Celsius and the other heated to 1 degree Celsius. The borders here are insulated. So what happens now, instead of having the temperature approach 0, instead the temperature will approach the average temperature of the sheet from the initial state. After all, the heat that is present isn't going anywhere, the boundaries are insulated, and so instead the heat will distribute itself throughout the region, in this case a square. Now for this, all of these animations were created in MATLAB using nothing more than slightly modified code that we saw previously when we were looking at the code for heat conduction and diffusion, but only in 1 dimension. Now you'll recall that previously we pointed out that we require that alpha delta T over h squared is less than 1/2 for the heat equation, and C delta T over h must be less than 1 for the wave equation. But even if it's close to this value, well, it will converge to the solution. Convergence is a little shaky, as you can sort of see below in the image, where the ratio is far too close to the value 1/2. That is why previously we actually chose an appropriate value of h, or delta t, so that the left-hand ratio was closer to 1/4 and the right-hand ratio was closer to 1/2. So in this example, we have an H-shaped room which is assumed to initially be at temperature 0. We're assuming that all of the walls are insulated and someone then turns on the heater at the location indicated at the red dot. Well, over time you do expect that heater to heat up the entire room. However, you also expect it to heat up the hallway closest to the heater much more quickly. That's what we're seeing in the animation on the right-hand side. You can see how the room is indeed getting warmer, first initially closer to the source of heat, and later you can see the heat is traveling down the hallway and heating up the balance of the room. All right, here we have an insulated room with a single heat source that you can already see that is at 20 degrees Celsius and a heat sink, or say an air conditioning unit, that is maintained at 0 degrees. You can see that point there too. The walls are insulated and the room is initially at 0 degrees Celsius. But as you can see, the temperature in the room is slowly increasing. And of course, it is increasing more further away from the heat sink and closer to the heat source. In fact, the heat distribution is going to ultimately converge to a solution to Laplace's equation. So here is the solution to Laplace's equation in 2 dimensions, where you have 4 insulated boundaries and one point that is maintained at 0 degrees Celsius and another that is maintained at 20 degrees Celsius. So as you can see, it's much more comfortable to be around the point or the heat source where it's closer to 15 degrees. So here we're simulating having a drop of water just coming into contact with the surface of water in a square region where the walls are, of course, insulated. As you can see, initially the wave goes out and strikes the walls and bounces off, as one would expect. Of course, because the wave is striking off the wall at different points, it becomes a little chaotic after a while. You can still see the symmetries in the water waves, but it's not very pleasing. Now here we have boundaries that are circular as opposed to square, but still insulated. And as you can see, the wave goes out and comes back. And in the center, it actually seems to now reform as a divot, which then goes out again. So you can try this with a coffee cup even. Try it yourself, see what happens. See if you can watch the wave go out and come back, but then return as a trough. Now, what's interesting here is the boundary is not really circular. Remember, we are only approximating a circle with a grid. And in this case, it's a grid where there seem to be approximately 60 subintervals in each direction. So the boundary is not really a circle. It's actually almost as if it was made out of Lego, so squares. But nevertheless, we still have a reasonably good approximation of how the wave goes out, strikes a boundary, and returns. Now here we have 3 simulations of the heat equation in 3 dimensions. So in the first case, we have a point source of heat. In the second case, we have a line of heat against a wall. And in the third case, we have a wall of heat. As you can see, with the single point source of heat, the heat does radiate through the room, but it doesn't do so evenly. the line of heat is better, and the wall of heat is even better, more so. You may recall that the ancient Romans heated their buildings by having the entire floor heated from below. In many farming communities from 100 years ago, you did not have a fireplace, if possible, but rather you had a stove that was the height of the entire room. This would ensure a more even distribution of heat, but of course, such a stove would be much more expensive than a simple fireplace, which would be more akin to a single point source of heat. Now here's a simulation of a resonance chamber. For those of you getting into radio frequencies and antennas, this should be interesting. A resonance chamber is a spherical, metallic, hollow item to which you apply a voltage to the exterior. And if the frequency is correctly matched with the diameter of the sphere, you get a huge magnification of that signal at the center. So if you take a look at the left-hand side, or left-hand image, you will see that there is a bright green, light blue area in the middle. You will see that it is pulsing sinusoidally, and that is the result of that magnification. This is because on the left-hand side, the frequency and the diameter of the resonance chamber correctly match. On the right-hand side, on the other hand, the frequency is off for this particular diameter, and therefore you can see that there is, yes, a voltage throughout the interior of the sphere, but there is no significant magnification. So this is something you will be looking at in your fourth year courses. However, here we're simulating it. And once again, it's not a sphere that we are using at the exterior. In fact, it's again a three-dimensional grid, and we are deciding which points are in the grid and which points are not. Those points outside the sphere are considered to be insulating boundaries. No, they are Dirichlet boundaries given by the sinusoidal voltage that is applied to the exterior. You can even observe this with the code we previously wrote to simulate the wave equation in one dimension. Here we have two Dirichlet boundary conditions, but where the boundary conditions are sinusoidal. And on the left, with an appropriate choice, you can see that the signal, which is reasonably small on the outside, is actually magnified on the inside of the string at the center, whereas on the right-hand side, with a poor choice of frequency for this distance, yeah, you occasionally get some large waves, but then later those waves get cancelled. So on the left-hand side, you see resonance. On the right-hand side, you do not. All right, following this topic, you now are aware that the heat and wave equations can be simulated in 2 and 3 dimensions. You understand that we start with an initial state at time t0, and on an appropriate grid, we estimate the state one time step into the future. Again, many of the properties are the same, and we have seen numerous examples of this in both 2 and 3 dimensions for both the heat equation and the wave equation. We did not look at implementations. However, it should not be too difficult to take the ideas we've seen here and finally put them into code. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!